The periodic table gives you a lot of assistance in figuring out how many valence electrons there are in a particular covalently bonded system. So let's consider BrO minus. So really what you're looking at when you see this is that you have a bromine, an oxygen, and a minus charge. And these are all clues as to how many valence electrons there will be in the final system. So let's go look at the periodic table and figure out from it how many valence electrons come from the bromine, the oxygen, and from the minus charge. So when I look at the periodic table, I see that oxygen's here. It's 1, 2, 3, 4, 5, 6. It's in the 6th column. It has 6 more electrons than the previous noble gas. So since it's in the 6th column, I can say that it has 6 valence electrons. So the oxygen contributes 6 valence electrons, I should say, to the molecular system. I'm not going to count those first 2 electrons, the ones that are in the core. And the reason why I'm not going to count those is because they're not really involved in bonding. They're held fairly close to the nucleus, and the attraction between the positively charged nucleus of oxygen and those nearer to electrons mean that we're really not going to be able to access them. And they're not really going to contribute to any of the chemistry of oxygen. For bromine, I can look up bromine. Bromine is in the 7th column, again. So that means that it has 7 valence electrons that we'll think about. So bromine has 7 valence electrons, and oxygen has 6. And the minus charge is -1. So this -1 charge means it has an extra electron above and beyond the bromine and the oxygen. So I would count this as 1 electron, and now I'm going to add these up to get the total valence electrons. So 7 plus 6 plus 1. So this thing has 14 valence electrons. At this point, you're probably wondering why we would ever bother to calculate that. And the reason why we bother to calculate this is a covalently bonded system. These are both nonmetals, right? Bromine is over here. It's a halogen, so it's a nonmetal. Oxygen's over here. Both of these are on the right-hand side of the periodic table. They're in this nonmetal region. If you see 2 nonmetals together, that means they're involved in sharing electrons. They don't have ionic bonding. One doesn't steal from the other. So what that means is that we have to figure out how they share electrons, how many electrons they're sharing. And to do so, we're going to use what's called the octet rule. And the idea behind the octet rule is that these elements all want to have enough electrons surrounding them so that they have a noble gas configuration. So oxygen, which starts off with 6 valence electrons, actually wants to have 8 valence electrons. It wants to have the same number of electrons around it as neon. So if it can somehow share enough electrons so that it has 1, 2 more electrons, it'll have 8 total valence electrons around it. Notice I'm not counting the core ones. I'm not counting these 2 from helium. So it would have 10 total electrons, or 8 valence electrons, ignoring those 2 core ones. And that's what it wants to get through sharing. Bromine wants to get 1 more electron, 1 more valence electron, so that it has 8 total valence electrons. And those 8 would make it have the same electronic configuration as krypton. So with that in mind, we can actually do a little bit of math. And what we're going to do is we're going to figure out how many electrons total the bromine and the oxygen or any other covalently bonded elements in this molecular fragment want to have, and then we're going to figure out how many they have, and we're going to figure out the difference. And that will tell us how many will be involved in bonding. So both the bromine and the oxygen want 8 valence electrons. That means that in total, they want to have 16 valence electrons. But between the bromine, the oxygen, and the -1 charge, -1 meaning that there's 1 extra electron around, there's 14 valence electrons. So they have 14. So if I take the difference and figure out how many electrons they're going to need to share in order to get 16 total versus the 14 that they actually have, I would end up getting that there's 2 electrons. These are the electrons that are going to be bonding electrons. Since each bond is 2 electrons, that means that there's 2 divided by 2 equals 1 bond. So this should have 1 bond. So if I was to write this out just using this math, I would write that there's a bromine and there's an oxygen. They have 1 bond between them. So if 2 of the electrons are involved in bonding, and I start with 14 electrons, that means that there are 12 electrons not involved in bonding. These are lone pairs that surround each of the atoms. So far I've written out 4, that's 6, 8, 10, 12. Okay. So let's go through this and just make sure that everything makes sense. Because a lot of times when I'm taking an exam, and when you're taking an exam, you want to have multiple ways to check things so that instead of getting 80%, you get 95%, and you're done for the, you get your A. So first check, does this thing have the number of valence electrons we claimed it had? Let's just count them up. So there's 2 electrons here, 4, 6, 8, 10, 12. That's 12 non-bonding electrons. And this dash is 2 electrons that are shared between the bromine and the oxygen. So that's 14 total electrons. So we know that we haven't violated that. 14 valence electrons makes sense. The next thing we can check is to make sure that each of these elements has a total of 8 valence electrons. So for the bromine, I count all its non-bonding electrons and any bonding electrons it has, and it should have 8. So this bromine has 2, 4, 6 non-bonding plus 2 bonding electrons. So that's 8 electrons total. So it wants to have 8, and it has 8. So we got that right. How about this oxygen? The oxygen has, again, 6 non-bonding electrons and 2 bonding electrons. So that's 8 total. So the octet of the oxygen is also filled. So this is the Lewis dot structure for BrO minus.